Good afternoon. Thank you for joining me today. I'm going to look at the basics of board game AI programming by looking at the way computers are programmed to play a certain class of board game, specifically those games that fit into the category of combinatorial games. We'll get into the applications of this method beyond that strict definition, but let's start simple by defining what a combinatorial game is, how we can get a computer to evaluate a combinatorial game and help us solve it. So first of all, combinatorial games is a term that was coined by John Conway in his 1976 book On Numbers and Games. Conway and his research partners defined this class of game with the requirements that you see on the slide. A combinatorial game in this 1976 definition must be turn-based. Each player makes a move in turn, not simultaneously. Combinatorial games must be two-player games, but the principles can be applied to games with more players. There's a little bit more complexity there, but once you are comfortable with this method, you should be able to adapt it in that way. A combinatorial game has perfect information, meaning that all players have access to all information about the game state at all times. There are no cards that are hidden. There is no information that is hidden from either player in a perfect information game. And finally, combinatorial games don't have a random aspect to them. There are no dice, no cards, no other source of randomness. All of these criteria are important because they allow for a purely mathematical analysis of the game, complete from start to finish. To perform this analysis, you need to understand the possible positions in the game. A position in this terminology is a legal game state. For example, a game of chess can be understood as a series of moves that lead from the starting position to the end of the game, with each move resulting in a unique position. To reach new positions from the starting position, you need to understand which moves are legal. So your computer program must understand the rules such that you can identify every possible move from every position. Finally, you have to understand how to win in order to analyze the game. The winning conditions need to be understood so that positions can be evaluated to see whether they are an end game state or not, and to determine which player wins. So some examples of combinatorial games are here up on the slide. There are more complicated combinatorial games as well. A few years ago, I implemented an artificial intelligence using this method for Neutron, which is a game of this type that has a neutral piece available to both players. And that piece is moved separately in between moves from the player's regular moves with their regular pieces. So that's kind of a weird game. The techniques that we'll talk about here can be also applied to games like this and extended to other games that don't meet the definition as well. So we'll talk about adapting your code once we've been through the basic method of dealing with a game that fits the strict and simple definition of a combinatorial game. So how do we get a computer to analyze and play these games? Let's start by looking at how we conceptualize the analysis of the possible future states of the game, because that's what allows us to identify the best possible move to make based on these options. So the tool that mathematicians use to visualize this analysis is a game tree diagram. On this slide, you can see a game tree for an almost complete game of tic-tac-toe. Every node in this tree represents a possible position or state of the board. So from the first position, there are 3 possible moves for X. And that's why we see 3 nodes in the layer under that starting position, okay? 1 node for each possible move that can be made. The next layer, once X makes that move, there are 2 spots left on the board for O. So there are 2 possible moves. So you can see that each of those 3 nodes in the first layer has 2 child nodes in the next layer down. Okay. And then after that, we're at end game. Either we have a winner, or we are going to end up in a draw. So the final layer of this tree has only 1 node or 0 nodes descending from the node in the layer above. It's useful to look at a simple example like this to understand the principle. Okay, and you can see here that the scores for end game states are also noted on the game tree. So in this case, we're looking at this game from X's perspective. X has the move in the first node. So from X's perspective, a win for O is categorized as a -1. A win for X is categorized as a 1, a positive value. And a tie, a draw, is categorized as coded as a 0. The reason that we need to provide numeric scores like that is so that we can evaluate what the outcome is and what its value from the perspective of the player that we are evaluating the board for, what its value is to them. So a win for the other player has a negative value. A win for the current player has a positive value, and a tie has no value. Before we get deeper into this, I want to talk a little bit more about the complexity. Okay, I touched on it when we started talking about this slide. This is a really simple diagram because we are at the end game. Okay, we are looking at a board that is almost finished. If you started at the top with an empty tic-tac-toe board, your first layer would have 9 nodes, 1 for each spot on the board. The layer underneath that first layer would have 8 nodes, and so on down the line until you finally get to those leaf nodes at the end that represent a finished game. So when you think about it in those terms, you can see that a game tree gets very complex very fast. Related to that, I wanted to touch on the concept of a solved game. Using the tools that we've already discussed, mathematicians declare a game solved when the outcome can be predicted from any starting position. Tic-tac-toe is simple enough that a person can solve it with very little experience. In fact, school kids do this in real time as they play tic-tac-toe with their friends for the first time. But games as complex as checkers or Connect 4 are also fully solved. There are 3 different levels of solved. An ultra-weak solution proves whether the first player will win, lose, or draw from the initial position given perfect play by either side. Perfect play means that the player always chooses the move that leads to the best possible outcome regardless of their opponent's moves. Okay, this solution doesn't require any actual moves to be described. It's an analysis, a conceptual analysis of the game and its legal moves. Okay, that's an ultra weak solution. A weak solution is an algorithm that can produce a win for one player or a draw for either against any possible moves by the opponent from the beginning game state. Okay, you have to start at the beginning of the game in order for that algorithm to work. A strong solution is an algorithm that can produce perfect moves from any position, even if play has not been perfect from the beginning of the game. So the brute force solution that we're looking at today produces strong solutions for the games that it analyzes. This list of game sizes helps us to understand why the brute force method works better for some games than others. Increased complexity brings more possible positions, which can quickly become unmanageably large. Even a computer has a limit to how many operations it can do in a short period of time. One way to get around this is to partially solve a game. For example, some computer chess programs use strong solutions to choose moves in the end game once most pieces are off the board. A chessboard that only has a handful of pieces on either side is subject to a lot simpler analysis than a chessboard at the beginning of the game with all of the possibilities still in front of it. So, so this method is used even in modern day chess programs in order to deal with endgame states. Even tic-tac-toe has more than 250,000 possible states in its game tree. Not trivial. Not trivial, certainly, if you were going to analyze it on paper, but a computer can make pretty short work of it. Okay, so the tool that we are actually using is the minimax algorithm. Okay, we're specifically using a variant called negamax. Not important distinction for this discussion, for the kind of getting your feet wet, but it is good to know if you decide to do further research. That's exactly the variant that we are implementing here today. So the minimax algorithm was first theorized by John von Neumann in 1928. And it consists of the proposition that for every two-person zero-sum game with finitely many strategies, okay, sounds a lot like our definition of a combinatorial game, there exists a value V and a strategy for each player such that you can maximize the best payoff for one player and minimize the best payoff for the other player. Using this idea as a starting point, the algorithm was developed in the 40s and 50s using the tools of combinatorial game theory to evaluate the game tree and determine the available move that will lead to the best end result. The basic idea is to anticipate your opponent's best response to every possible move and select the move, your move, that minimizes the options available to your opponent. That's the goal. The goal is to eliminate their best moves by making moves that that limit the gains that your opponent can possibly make. Okay, so we can take a look at the demo. There's the URL there on the slide, the demo of this code. It's an implementation of tic-tac-toe on the web. And you can check out the code on my GitHub, okay, and the URL is there. This game uses minimax to make moves, and let's walk through the components of the algorithm before I dig into the code. These methods, okay, are the methods that provide the basic functionality required by minimax. We have a class named board, okay, and that class implements the game board itself and the methods required by minimax, okay. The game over method evaluates the board state to see if the game is over, and if so, who won. It returns a 0 for a game in progress, an integer representing the winning player, or a 3 if the game is ended in a draw. The possible moves method returns a list of available moves for the current state of the board. And finally, the move method takes the X and Y position of the move to be performed, adds it to the current board, and calls the next turn method to advance to the next player's turn. This code is written in a modular way. All of the code that manages the game state, the game rules and victory conditions is separate from the minimax implementation itself. So without too much trouble, you should be able to adapt this code to play a different game by replacing these methods to reflect the configuration and rules of the game that, that you want to implement. But if you're planning to use it for anything much more complicated than tic-tac-toe, you're going to want to add some refinements. So at this point, it's probably fruitful to take a look at the code and just review the board class and its methods before we go any further. So I'm going to do that. Here you go. Okay, you should be looking at the GitHub page for Minimax. There are a whole bunch of components here that I'm not going to talk too much about. There's the license file and the README file, which are more or less required by GitHub for a complete repository. Index.html is the web page that loads all of the other assets, all the other components, and presents a user interface to the end user. Main.css contains some styling to make the web page look a little bit nicer. And main.js is the game implementation in terms of user interface. So the main.js file contains all of the JavaScript that deals with the interaction of the user, all the user's choices that it makes on, that the user makes on the web page. And main.js instantiates objects from minimax.js. Okay, the code here is a little messy in main.js, and the reason for that is that the web page itself is an old demo for a course that I taught years ago for a two-player game of tic-tac-toe. And in order to prepare for this event today, I wrote this code to adapt the existing tic-tac-toe game to support artificial intelligence. So there's a little bit of messiness where the two solutions mesh, and that's all kind of hived off in main.js. So taking a look at minimax.js, which is what we're really interested in here. Here is the board class. Okay, it's got a few properties that are valuable. The size property identifies the size of the game board. So in this case, we are expecting a game board that is symmetrical. It's the same width as it is. It has the same width as it does height. The array of arrays defined in the positions property is the representation of the state of each spot on the tic-tac-toe board. So you can see there are three arrays of 3 integers. They are instantiated as 0. They are initialized as zeros, but they can contain contain also integers to represent which player has played that specific spot on the board. So a game in progress will end up being filled with a mix of zeros, ones for X or player 1, and 2s for player 2 or O. Okay, we also have a property that identifies what turn we're on. And in this case, the turn property indicates which player's turn it is. So you can see down here a simple method that advances to the next turn, and if advancing the turn results in a number higher than 2, we revert back to 1. So we toggle between turn 1 and turn 2 for the 2 players. The possible moves function basically just looks at the current state of the board and returns all the positions that are empty. Okay, we have a nested loop here, loop through the array that represents the board, and we look for zeros. And every 0 that we find is a possible move. So we add it to the array. Then we return, when we're finished, we return that array, which lists all the choices that a player would have at that moment, given that board state. The game over method, in this case, how do you win at tic-tac-toe? Well, you either fill a column, a row, or a diagonal, or an anti-diagonal with markers of either the X for you or O for your opponent. So we just have to check, we just have to brute force it. We check every spot on the board and check whether or not the winning game state is the conditions of a winning game state have been met. Okay. We also have to handle the special case of a full board, and you can see that a full board we return a 3. Okay, we'll take a look at what that looks like a little bit later, and the reason for that that this method can return a 0, 1, 2, or 3. 0 is a tie or no decision yet. 1 is a player 1 win, 2 is a player 2 win, and 3 is a board full situation. Okay, you can have a draw, you can reach a draw before the board is full. So those are 2 separate possible conditions. And finally, we have the move method, which is the method that we use to actually apply a move to the board. Okay, and we simply take the numeral that represents the current turn, and we assign that value to the position that has been specified as an argument to this method and advance to the next turn. That's it. So all of those methods, that's the minimum that we need in order to provide our algorithm what it needs to evaluate the game and determine the optimal move for the next player. And we have a utility method that just displays the current state of the game. Okay, when if you're looking at the JavaScript console while you play the tic-tac-toe game, you can actually see the board state reflected in the console with every move. Okay, so that's the board object, or the board class, which instantiates an object when the game is played. And one thing that I want you to keep in mind here is that this little class with its array representing the board and its methods is not instantiated once in this code. It is instantiated thousands of times by this code. So at any one time, we won't have one instance of the board class in place. We will have hundreds or thousands, and I'll get to why in a moment. Okay, so let's go back to our slides for just a minute. And just review what minimax will do. Okay, there's the game tree again. The max method itself, and the method is called max in our code, is an implementation of a recursive algorithm for evaluating all possible future board states. Let's walk through the code to see how it works. Okay, so I'm going to describe it, and then we'll look at the code. The max method takes 2 parameters, a board object and an integer that reflects the current depth of the tree. How many moves ahead of the current state are we evaluating? That is the meaning of the integer that gets passed to the max method. When called by the game, in response to a player move, this number is always 0. Let's take a look at our code. Okay, and here is the max method. Okay, and there's those parameters that we were talking about, the board parameter and the depth parameter. So the board object is passed to max along with the depth. So when the method is called in response to user action, this is always the current game state after that user's move and a 0. So the first thing that the method does is check the state of the game on this current board. If the game is complete, it returns a 0, 1, or -1, depending on the outcome. Just like we saw in our tree, 0 is a tie, 1 is a win for the current player, and -1 is a loss for the current player. Okay, we do that evaluation right here. If the game isn't over, then this method gets a list of possible moves on the current board. Okay, and what you're going to see here is that we're doing a couple of things. We're doing a couple of things in JavaScript, and this is not a JavaScript tutorial. JavaScript happens to be the tool that I used because I wanted a web-based implementation of tic-tac-toe. But in order for this code to work, we have to be dealing with unique copies of both the board object itself and the possible moves, because those two things in our code are two separate entities with two different sets of properties. We do that in different ways. The possible moves, the values that are returned from the possible moves method are an array. So we copy that array, okay? We copy that array. But when we are dealing with the board object itself, that is a JavaScript object. So we have to clone it, okay? Again, this is not a JavaScript tutorial, but if you're interested, there are two utility functions here that are pretty simple, and those two utility functions do the things that we need to do for this algorithm to work. So if you are working along at home and you decide that you want to try to implement this yourself from scratch, just keep that in mind, that if you do it in JavaScript, you're going to have to deal with that. Okay, so we loop through our list of moves. Okay, then we create a clone of our current board, apply that move to the new board that we just created, and then calls max itself. Okay, it calls max itself at the next depth down. So the cloned board and whatever the depth that got passed to this method is incremented by 1, and the cloned board with the new move applied is passed to this method. Okay, and that method will recursively call itself. It will continue to recursively call itself until it reaches an endgame state. Okay, and when it finally reaches an endgame state, we will get an outcome. Okay, and we simply evaluate whether the outcome of that entire sort of set of nodes that descend from the one possible move that we have in front of us, if the outcome of all of that is the same as the best score that is available to us, then we add it to the list of the best possible moves. If it's better than the best score that is available to us, then we create the empty array that represents the best moves and add this move to it. So what we'll get back from this method, okay, is dependent on what happens in the course of executing this algorithm. The method returns either an integer representing the board state if it's an end game state, or an array of possible moves. So this requires a bit of code to manage it in our game JavaScript file. A nicer implementation might return both the moves array and an integer indicating game state every time it's called. But this approach is fine for our tiny demo. And if you're interested in tinkering with this code, that's something that you might implement as an exercise for yourself. So this, this small method combined with the power of recursion, okay, and all of the supporting methods that we created for our board class is all that is needed to play winning tic-tac-toe. Okay, so let me demonstrate that for you. A few things that are interesting here. This is what the game looks like when you start it. If you pop open your browser's developer tools, and let's see, what we want is the console. There we go. And you open up the console, okay? You can observe the progress of the game. And you can see the debug values that are that are sent from the game to the JavaScript console. But you can also do fun things with it interactively because you have all of the tooling loaded. You can create your own board objects and interact with them right here in the browser. So we've got some sample code here at the bottom of our minimax source file so that we can do some testing. Okay, so let's take a copy of some of this stuff, and there we go. Paste it into our JavaScript console. Okay, so we can instantiate a new board, define it. So in this case, this board is almost full. There's only one legal move available to it. It's X's turn. We show the board, and then we get back, here's what show moves does for us. We're getting back an array that contains only the value 0, 0, because that is what is left on the board. That's what's available, that one spot, okay? Then here, a few lines down, we create a completely separate board, and you can see it represented here. And there's the list of possible moves, okay? So that's how the board class works, and that's how you can interact with it. You can mess with it a little bit interactively, and that will help you in your testing. Again, I think there are some real opportunities to take this code and play with it and adapt it to something that is useful to you. Let's talk a little bit about what those possible refinements might be and how you can take this simple demo and extend it into something that is useful for you in a game project of your own or some other application. And I just want to give you some hints here, okay? I just want to give you some hints here about some stuff that you should consider and some of the issues that you're going to face. The number one thing is a limit on search depth, okay? The tic-tac-toe tree is small enough that the JavaScript interpreter in your browser can store it all in memory and evaluate the entire tree in very little time interactively when you click the page and choose a move. It's a tiny problem. But if you are building an application that is going to play a more complex game, the game tree could become unmanageably large very quickly. Okay, it will become unmanageably large very quickly, and you're not going to be able to evaluate the entire game tree for every move that is made because it would just simply take too long in between moves. there was I'm old enough that I had an Atari 2600 as a kid, and the Atari game that played chess had difficulty settings. The more difficult you set the game of chess to be, the longer it would take that chess program to select a move, because you were selecting a different depth, a different search depth for the game tree. So when you limit search depth, though, you have a big problem. And the big problem is that most of the terminal nodes in your tree that you examine are going to not be endgame states, okay? Let's say that you decide that your chess program can look 3 moves ahead, okay? It's going to evaluate all possible states of the board 3 moves ahead every time a player makes a move. Unless you are 3 moves away from the end of the game, you are not going to see an end game state in any of the terminal nodes in your game tree. So how do you evaluate the boards in that situation and return something that is useful to the program? And the answer is that you have to develop some kind of a heuristic for board evaluation. You have to figure out some kind of set of rules that can score a board, okay? And this is where you have to be a little bit creative, and a good heuristic can be the total difference between an AI that feels satisfying to a player and an AI that is worthless, okay? You have to effectively evaluate an unfinished game and provide some kind of heuristic method for the algorithm to be able to identify the relative value of the different moves. And one way you might do that in chess, for example, would be to evaluate whether or not a piece is taken, okay? So if you write a chess program that is going to look 3 moves ahead and prefer moves that don't result in the computer player losing a piece, then you're going to have to, the human player will have to be able to look 4 moves ahead in order to maneuver the computer player into losing pieces. That's essentially what that means. And that can work pretty well. I've implemented heuristics. I mentioned Neutron before. I had to implement heuristics for Neutron. And you know, as you tweak and refine it, it's really interesting to watch the game's behavior change as it gets better and better at playing the game, as you're feeding it better and better information. Another method that is really important to talk about is called alpha beta pruning. And this is a method that is almost as old as the minimax algorithm itself. And essentially, what alpha beta pruning does is it allows the minimax algorithm to ignore whole subtrees, okay? And the way that it does that is by evaluating whether or not the immediate result of a move is going to be worse than the best move you already know. And if that's the case, then we can stop evaluating the rest of that branch, all of those nodes, because the solution does not lie there. A better move is not going to be found underneath a worse move. And what implementing alpha beta does is it essentially doubles your ability to search depth. It doubles the depth of the game tree that you can search, more or less, because it eliminates slightly less than half of the nodes that would need to be evaluated. So a really important thing to look into if you decide to implement this seriously for any application beyond a toy like tic-tac-toe. You correspondingly, you can also identify with your heuristic promising game states. Okay, game states that are likely to be promising, and you can identify that with whatever methodology makes sense to you. Identify a promising game state, and when you meet those conditions for a promising game state, then you can exceed your depth limit. So the combination of these techniques will result in an asymmetrically searched game tree where stuff that is clearly going to produce a better result gets searched more exhaustively, and stuff that is clearly going to produce a worse result gets searched less exhaustively. And the last thing that I want to mention is the ways that you can adapt this solution for non-combinatorial games that include a factor of randomness, games that include imperfect information. You are no longer able to use minimax to fully predict the outcome. Okay, that's impossible as soon as it's not a combinatorial game. But if you in your heuristic account for probability, okay, account for the probability. So for example, in a board game that is a simulation of a war game, some war game type simulation, then you might have a 60% probability of hitting your opponent when you fire your gun from a particular location. Okay, that 60% probability needs to be baked into your board evaluation. Okay, so as long as the probability is known, then you can adjust your evaluation of the board state by weighting according to those probabilities. And imperfect information, if you don't know, if there are things that you don't know, you can also implement a heuristic to evaluate what possible things might happen. So for example, if a game has a set of cards and we don't know what cards our opponent has, but we know what the possible cards are, then we can evaluate future states of the board based on the assumption that the player you're opposing has the best available cards. So if you make an optimal play based on your opponent having the best available cards, then you are likely still to reach an acceptable result in the case when your opponent has suboptimal cards. So those are some of the things that you can explore in order to take what you've got here on this GitHub page, this sample code, to take it and to make something that's your own, to make something that is useful and effective. And I think that what has been provided here is a decent starting point, but you're going to want to do some further research, and you're going to want to look into these particular options as a way to make what you're doing better and more effective. And that is that's the conclusion of my presentation.